Here in Birmingham, England, and we're at the Printwear and Promotion Show 2012. It's February, and I'm just going to do the presentation on what is laser. Go ahead. So in simple terms, it's an invisible light energy, and it's focused and it's concentrated and it's invisible, and when it hits a surface, the energy is being dissipated basically. So it's always following vector lines. Whatever you create in vectors is what it's following. And if, for those of you who are new to the industry, vectors are the outlines, the shape of absolutely anything. You can think of it as essentially a heat spot where you're focusing something tiny. The best example is if you ever took a magnifying glass and you use the sun to focus on newspaper, or some of you focused on ants. Yeah, that's right. There's got one in the crowd who really burned a lot of ants. Go ahead. So think of the beam, typically laser, which means light amplified, simulated emitted radiation. The light that's coming from the ceiling or the projector is expanding out, and laser light is projected to be narrow, and then the lens that you put it through actually makes it very sharp. And then when the light energy hits a surface, it essentially vaporizes it or makes it disappear or go away. In this case, you could be engraving and cutting out a shape. You could be taking off a surface, taking off a layer. If it's something sensitive like textile, you burn right through it. Go ahead. If you want to make a visualization of a fluorescent tube in the ceiling light, laser would be created the same way. It's a type of gas. CO2 is the most common laser used for cutting in the textile industry. And if you buy a USA-made one, I don't know too many others in the world. The top ones in the world, even in Europe, are being purchased out of the USA. They will last 20,000 hours to 25,000 hours. In a business that's like textile related, that's somewhere between 4 and 7 years on average, because you might be zapping it for 2 seconds or 12 seconds times 12 pieces or 100 pieces. So it's the time that the laser's on that you're counting as the time that it's used. In general, the top quality lasers don't just die. You will find the ones that are made in Asia are very inconsistent. The power fluctuation is very different, and they just die quickly and you have to replace them. Here they're a lot more expensive. They last a lot longer. They don't generally die, but they will fade away. So when you hit that 20,000, 25,000 hour mark, you have to use more power, more time to get the same effect, right? So the three predominant ones in the United States and around the world, in no particular order, are Universal. They are out of Arizona. Coherent, I want to say that's in the northeast of the United States, and Sinrad's in Washington State. And that tube is covered in a housing with electronics, and then it's cooled, and typically air-cooled. Liquid-cooled lasers are a lot more expensive. You need a chiller. You have to pipe in fluid like in a radiator. But in general, air-cooled are more than adequate, and they work in the normal room temperature environments all around the world. This is the Sinrad box. Go ahead. The types of laser that are most common are CNC, which stands for computer numerically controlled, plotter laser, which is table going along an X and Y axes, and also known as the tabletop. And here is a close-up that somewhere down here is the laser tube, and then the laser light is reflected with mirrors up into this area where there's so-called the gantry, and that device moves left and right and back and forth, which is the X and the Y axes. And up close there's some sort of system to pump air to push the smoke away from the nozzle or from the lens so that it doesn't coat it or cake it up, and then it's sucked somewhere back underneath on the sides, etc. And this physical device moves. The problem with some of the lasers, is there another picture coming up that shows it? The problem with some lasers, and again I'm not being selective on any brand, but I hear it all the time at the shows, is that on a plotter type laser, quite often the further away you go from the source, the weaker the laser can be. And that should be like a design defect or a quality with mirrors and quality of the laser beam, etc. But in general, if it's a very big laser, the furthest extremity from wherever it's coming out is an issue because it's not as strong as on the right-hand side. And here you see some sort of a honeycomb type of grill, and in general the air wants to be sucked down. So one of the problems is that if you have a lot of material that's thick, like let's say wood for example, the smoke can't get around and hits the lens first, and that lens gets caked up. So think of yourself as cooking eggs, and then cooking eggs and cooking eggs and never cleaning the pan. then you're cooking the cooked stuff, and that's what happens here. This lens, which is often the size of a pencil eraser, is very small. The distance that it's away from the surface is maybe a half an inch, and that gets plugged up. And when that gets plugged up, the problem is that you're losing energy, and the energy is being absorbed by the lens and not in the product, so the efficacy of the laser effect is less, and eventually you'll heat up the laser lens to such a point that it can break or fracture, or it gets so full of cake, you know, the mess from the burning, that it can't be clean and you have to replace it. Go ahead. So here you see on the side of the laser would be the laser source. It would hit a mirror, and then it would be reflected out into the area. And so as this moves back and forth, the laser beam still hits that mirror, and it still always goes in that direction, which is the x-axis. And then it's focused through a little lens, and it goes down, and it cuts out the word, the shape, it etches it. And the power of the laser was what determines what happens. So a higher power will vaporize more, a lower power will vaporize less, so you can scratch the surface or you can cut right through. You can go very fast with high power and make less damage, but takes more times to cut through, or you can go very slow, very high power and get right through. I'm going to do a couple quick videos here, just from the web, from different companies, and I'll show you the difference. So here you have a swatch of material in a flatbed plotter tabletop laser, and if you can see it, it's got a zigzag back and forth, and it only moves 1 millimeter at a time moving forward. So to do, you know, left chest logo, something like what's on my sleeve here, that might take 10-15 minutes. So I'm talking here, and it's still going on. It was started when we went in there, so it's already a few minutes. Can you just fast forward it and see how many minutes we have here? So let it go there. Let's start it over. So it wasn't even, with the portion I'm showing you was doing a small strip, maybe an inch strip, and it took a minute and a half to do that, and it might be a 4 or 5 inch strip, but I'm not exactly sure of the size relative, but that's one of the issues. Notice here, so it's a minute and a half, notice here that on a plotter laser it's a swatch of material. It's very difficult to take a jacket, to fold it, to get it into position, to lay it in, to know where, and then how to line it up so it's directly along a seam in a very specific spot, or exactly on the collar, or on the yoke. That's the challenge when you have a plotter laser. So even if you have a big plotter laser, you only have this little surface distance between the lens and the work area, so it's quite challenging to line that up. So people have tried. Sometimes people are able to get their hoop in there, but the hoop in the bottom of the shirt, there's a cavity, so you might be too far away. You have to adjust the lens. So it's a complex process, and at the end of the day, is it really worth it to spend 5 or 10 minutes to set up a piece where you're only going to get $3, $4 for that decoration, when in normal fact it should take you a few seconds. Go ahead. A bridge laser is the extreme of the technology. I'll go into how they work a little bit later. And what you've got here is a structure, a very large structure, and the whole yellow laser moves along mechanically. So it's complex. You're talking no less than $150,000 on average, $180,000 plus your container, your setup, your delivery, moving your equipment out, getting it installed, putting it above. So there's, you know, often a week or two process based on the size of the laser. The advantage is that you can register this laser to exactly that destination. So your embroidery hoop 1 has a 0, 0, your embroidery hoop 2 has a 0, 0, but it's a little bit different than head 1, etc. So this laser you can accommodate to match the embroidery machine's mechanical fault, because every embroidery machine is different. You can't take out a design of head 1, put it in head 3, and take head 3, put it in 5, and 5 and 2, halfway through and continue, because it won't line up. So the bridge laser compensates for that. The challenge with it is that it doesn't shoot out a visual beam. You just see the result. You can't aim. And then the table where you would etch is not set up to be conducive to high productivity for just etching services. Okay, but it's a valid technology. So here I'll give you a couple different examples of something different. When you can have a visual before you actually shoot the laser, then you can see where you're going to shoot and register something. Just make little increments forward for me. So you can also put a collar in there. You can visually see where it's going to go, and then you can exactly line it up, and that's difficult to do with any kind of laser unless you have some sort of physical visual. Or you can do the placket on where the zipper is, etc., and get it right along the spot. Here's an example when you have a visual. This person's doing leather chamois for cleaning cars, and they basically have sprayed stick glue down from the screen printing industry. The chamois sticks there. They throw the product on because they have a visual that they're looking at. You can't see it in the video, and then they hit the button, laser it, and there's turnover. So if you watch the video, it says here up to 210 pieces per hour. That's a big number, and that's what you can do in America and in Europe to have a big productivity range. Go ahead, go right about to here. So it's just a lot of video, but I guess they're proving that by staying at that speed to time it out, and see what else is right at the end here. So now you're actually doing a finished garment like a hoodie or sweatshirt in the hoop of an embroidery machine. There's nothing exciting about a needle moving. But once that's done, you take out the hoop and you literally plug it into the laser. This is an alternative to the bridge technically. And you have the same hooping arms as on your embroidery machine. Oops, we just missed it. Okay, so just go to the next video. And what you're doing is you're cutting around that area and actually taking it, putting the next one in and cutting the next one. So just move half an inch there. So here's a finished product where you will take a piece of applique, lay it down on the sweatshirt. The red one was a reverse applique where you cut into the sweatshirt. Now I'm putting something on top. I'm stitching it down, and then I'm actually tracing it with the laser. So I see it, I can register it. If I'm going to do one piece of the sample, it's easy to do. If I'm going to do multiple pieces, it's registered with the embroidery head. And then that white stuff is the laser cutting through, making a pattern. So you can see that it's passing through a few times. And you see flame here, but don't freak out because the flame is showing the after effect. The laser's already left the territory. There's nothing left there. So it's pretty safe. If you cut the material approximately 98–99% through, you can avoid using foil. And as you tear it away, you end up having a distressed look on the garment. So it's kind of interesting to do that. And remember, the big thing is that it's off the embroidery machine. The stitch count is low. It's off the laser, away. Next thing is going in. That's happening on a minimum wage cleaning table. So you have productivity. So if you have less embroidery heads, you can get 4 to 6 times more output without having to get more embroidery heads. And in the industry, the average in North America is about $35, $45 an hour. That's the finished product. And in Europe, we're finding out that's like 25, 30 euro. In the UK, 25 pounds or so. That was reverse applique. Now here, we're actually doing the same thing again, where we're putting a layer on top and we're cutting it out. Oh, sorry, that was reverse applique. So there's that fluffiness underneath the t-shirt or the hoodie, and now they're running stitching it so it's attached, but they're going to cut inside the letters, and then you're going to remove the inside out. So this is identical to the burgundy one, and you're going to be left with the piece that's showing through, and that's called reverse applique. So it's kind of exciting when you watch it, but it's very quick and it's almost instantaneous. Now, in a lot of cases, if you want to do it right, you have to put foil underneath. And I'll show you a test coming up in a second, how to determine when you use foil in the laser embroidery process. Will they clean this out here? Waiting for the fingers. There you go. So he's cleaning it out, and there's foil underneath here. And the foil is critical because I can't afford to damage what's underneath, because you as the decorator have an issue if the shirts go out and they start to get defective. And what my example is, if you ever cut your jeans on a nail or caught them and then you wash them, the hole got bigger. If you poke a hole, we can go out of this video, when you poke a hole with a laser and you wash the garment later, then you start to create an effect that's a lot larger. So here's a couple different lasers. I did the tabletop CNC plotter laser. This is technically known as a single head or a fiber laser. And what you're doing is you have the laser tube that basically fires at full power through a fiber optic, and that larger tube often is the device that's sucking the smoke away or attempting to suck the smoke away, and you're firing the laser, which is being activated by the activity of needle 1. So as needle 1's moving at a high rate of speed, that's the trigger to turn on the laser, and that happens in this area here. So it's just a more cost-effective laser. In the industry, it's known that the average output for applique, reverse applique, is somewhere in the neighborhood of 4 to 5 applique per hour. So if you're in a retail environment where you can make a 30 quid profit, that's what they, 30 pounds sterling, or you can make a $40, $50 profit, then it's worthwhile for sure to have that laser to do that. Go ahead. So a scanning laser is the technology that's at the upper scale. It's the component that the bridge lasers use, and the main idea is that the laser is attached mechanically, sending the light beam of the laser beam into the scanner head, and I'm representing it in red always so you can see it on a presentation. And this scanner head has a set of mirrors in there that are wiggling to make the movement. So you're shooting out here onto the surface. Go ahead. Here's a representation of mechanically what's happening. You have a laser entering from some location, and there's a mirror on a motor, a mirror on the motor, and as it hits here, it gives you, let's say, the X direction, and if it hits the other mirror, it gives you the Y direction. So the combination of them together will make the movement. And then it always has to go through some sort of what's called fixed focal length lens, and that device on a Galvo laser can be the size of a Coke bottle, or Coke can, etc. And what that does is it takes the fatness of the laser and focuses it into a narrow point, and so when it's at an extreme, in a corner, in an edge of the radius of the area that's working, it's going to stay a fine point. So a good example is if you've ever taken a flashlight and you've aimed it straight down at the floor, you've got a perfect circle. But if I aim it on the floor at an angle, my circle turns into an oval. You familiar with that? Good. So I want to get a lot of nodding heads here. And when that happens, you are changing the energy because it's spread over a large area. This lens prevents that from happening, and that's built into the scanner head. It's nothing that you have to worry about as a laser owner. That's something that's taken care of by the laser manufacturer. Go ahead. So here's an example of the 3 different, they're not this big by the way, they're like the size of a finger or the size of a thumb, and the mirror can be, half an inch to an inch range depending on what we're doing. And that's what the motor looks like with the mirror at the end. They're a very specific type of material, so they have more than 99% reflectivity, etc. So every time you're bending the laser, moving it, putting it through a mirror on an angle, you're losing about 0.5% of power in general. Okay? So now it gets really complicated. I want you to memorize this as a test at the end. Here you have the incident laser, which is where the laser's coming in. And typically you're conditioning the beam in some way. You're making it cleaner, rounder, better, whatever. And you're putting that through the mirrors, which is the X and Y, those Galvo mirrors. And then you put it through the F theta lens, remember that fixed focal length lens, and then you have that surface. And a good representation is that it makes it narrow and sharp again down here. But what's interesting is that on a scanning laser, there's a great distance from the surface from where it's coming out. On a plotter laser, it's like this. On a fiber laser, it's like that. On a scanning laser, it's a big distance. So if your lens is this big, and you're thinking about a beam coming out, it's a long, narrow focal beam. So sometimes you can have product that's a little bit higher, a little bit lower, a little bit crooked, a little bit bumpy, and it's not affected by this laser. So you can have a quicker setup and not so much time invested to set it up perfectly. Okay, go ahead. So here's a picture of a laser that's probably 65, 70 feet long, and you've got multiple 12 or 18 head machines underneath it, and it's justified to make that expenditure because these are factories that have 300, 200, 600 heads of embroidery. Go ahead. Here's another angle. This one is from New York that I was involved in the installation with years ago, and it's the longest laser in the world. It's over 96 feet long, and there's 3 12 heads, 2 head, and a 6 head or something, all underneath one structure. So imagine it's like 3 times the length of this room here. That's good. If this is on video, 3 times the length of the room, nobody's going to know what that is. Go ahead. But long. Let's say long, right? So this is a standalone laser. This is a combination of scanning laser without the bridge. And the concept is that if you have a 6 head here and a 6 head here, you can take out the 6 embroidery heads and plug them in the hoops, and the laser is in harmony with the embroidery machine, and it knows it came from head 1, head 2, head 3, head 4, head 5, head 6. Machine A, machine B, it knows it came from that. So it does the same thing the bridge does, and you can put the machines on either side, and it's like a telephone booth concept. So it's just all the different lasers that are available out there. Go ahead. Now, this is a bit of my tongue twister. The things that are in red, I'll read them out for people who are at the back, and I'll read it out for people on the video who watch the video. What can you decorate with laser? Anything CO2 is unique because there's a huge variety of stuff. When you typically buy a laser for the embroidery textile decoration, its strength is not to do tiny carabiner pens and little trinkets and things like that. That's best left to, like, $6,000 tabletop laser, and that's a different business because the margin needs to be in volume, and that's not typically what I'm referring to or what this seminar is all about. It's about doing textiles and optimized for that decoration. However, there's a lot of things you can do on the side. So I'll list them off. Everything in red: cotton, felt, leather, micro fleece, micro dry, which is dry wicking, also known as performance wear, polar fleece, micro fleece, polyester, tackle, twill, and wool. In the UK, I got a lot of questions, and nobody's really familiar with tackle twill here. So there's a great company in the USA called Twill USA, and they carry all kinds of twills. They ship everywhere in the world. And tackle twill is a material that represents embroidery fill. And it comes in all the thread colors you can imagine. So instead of actually sewing out a whole area and creating the weight and the bulk, you can replace it with tackle twill. And it's the same stuff they use in North America on all the hockey jerseys and football jerseys. It's a strong material that looks like all stitch out, and you attach it with running stitch, zigzag stitch, or satin stitch. So that's interesting. But the other items, on the left side is cut and etch, right side's etch. Acrylic, anodized aluminum, bare metal, brass, ceramics, corian cork. Delrin, which is just a synthetic material related to bags. Fiberglass, glass, granite, marble, matte board, melamine, and metals. Metals has an asterisk because anything metal, anything reflective needs a coating so that you don't have the laser bouncing off, shooting different places. That gets dangerous. And also metals don't react unless there's a substance sprayed on it chemically. The laser reacts and creates heat and then creates and leaves a black mark in the metal. So stainless steel, titanium, brass, aluminum, they all need that spray that goes on there. Mylar, painted metals. When you have a painted metal, you take it off the surface with the CO2 laser. Paper, plastic, pressboard, rubber, stainless steel with the sprayed tile, titanium, wood, and wood veneer behave the same way. So often when you go around the shows, you'll see lasers doing that. You'll see different lasers specialized in different areas. But a scanning laser has the most versatility, the longest longevity in that respect, because it has the greatest distance from the surface, it has least exposure to smoke, it covers an area extremely fast, and we live in a world where we have to do stuff very fast. Go ahead. So here's an example of the process with a bridge laser where you've got a finished garment and you've got the blue felt, and on top of that you've got the beige. Here the beige has been cut, but it hasn't been peeled away, and I think the next step it walks you through the process. So you've got a hoodie with a zipper here. On the left-hand side of the chest, you've laid down a big chunk of felt, but you've put down the foil first, and I'll get to that in a minute. And the foil prevents the laser from wrecking the garment underneath, and now you've done a running stitch, and the laser has cut over it, and you're peeling the excess away, and you'll peel the foil away in just a second. Go ahead. So now the foil is being pulled away. Come on, we need to turn over here. People are going to fall asleep at home. Now you've got a bit of the foil that's remaining here. You can clean that out. It's a bit of evidence. And the next thing is you lay down another piece of foil and you put the beige on top. The reason you have to do it in this design, which you'll see in a second, is because you've got overlapping. You're putting the beige directly over top. If they're not overlapping, you could almost never have that issue. You could have put them down at the same time. And there's some samples out there, like the Subway sample, etc., that I can show you afterwards where you've done that. So here's the remaining pieces that's left over from the cut. Go ahead. I've pulled off the foil now. This is an example right here of how you know when to use foil and when not to use. I'm getting a suntan every time I walk in here. When you have a dollar store pointer laser, just a $2, 2 quid laser from a dollar store, what you're doing is you poke it against the shirt, the product that you want to laser cut. If the laser comes out on the other side, then you need to use foil because the light can get through. If you hold the material up to the light and you can see light come through, the laser is like smaller than a pin. It'll go through that little speck and it'll cause damage on the other side. So here I've got another material, I'm shining the laser through, and then I can see the dot exposed below. I know, or I'm shining it from the bottom up, I can see the dot. It's not black, it's not plastic, it's not solid. That means the laser light's going through. It means you're going to have to use foil. Go ahead. So here I'm doing it on a pink, and I'm shining it down. And here I'm doing it on that felt material that you just saw a minute ago. You can use wool or acrylic, but the wool tends to smell because it's natural. And it's not shining through like a sharp point, but a lot of the light is escaping, so it's a danger that you wreck the garment that's underneath. And you as the decorator have to be aware that you're liable if you do a job and it starts to fall apart with customers. Your customer looks bad, and you know, Murphy's Law makes sure it's always your big customer, not your loser customer you want to get rid of, right? Go ahead. So there's the final result, where I've got the blue felt, and then overlapped on top here I've got the beige felt, or the tan felt, with a contrast stitching. So this whole thing is less than 1,000 or 1,100 stitches, but you're getting $7, $8 for that decoration in a low volume. But you're doing it in a fraction of the time. So here you've got the finished product, you've got that first layer scrap and the second layer scrap. Yes, I'd rather have waste. Why? Because it's less cleaning time than if you've got too much preparation. What do you care if you're going to throw out 2 or 3 or 4 cents of material, but you're going to save, you know, basically, if you did it the old-fashioned way and cut it, you'd spend so much time it wouldn't be profitable. Or here you can knock off 40, 50 pieces in an hour, hands down, done, finished. Go ahead. This is Celtic Design. This is visually looking like they're interwoven and overlapping, etc. Be a total nightmare because it's so many individual pieces. 1, 2, 3, 4, 5, 6, 7. So there's, you know, in the neighborhood of 21, 28 pieces in that design with the scrap, and you got to include the outside. How would you do it? If you just lay it down, you do the running stitch, and then you do the laser cut, you can peel it off. You're in business. With tackle twill, you can just adjust the laser to the right number, so you literally don't have to use the foil underneath. Why? Because when you take a dollar store laser pointer and you shine it through the tackle twill, you won't see the light come outside. So you can just get away with little tricks like that. So this is taking tartan material that's like a wool or a cotton with a print on it. It's been tacked down with a running stitch. It's in the hoop. It's come out. I don't know if you can see it from over there. I can see the lines here where the laser's cut it. And what's happening is I can tear this off. Go ahead. I've removed it. And go one more. And when I remove the foil, I'm left with the word dance. And because this is like a cotton twill or that tartan, etc., it's already raggedy. So the joke I have is that I've had customers, there's some videos on YouTube, where they've taken a toilet brush and they've made it distressed. So my question is, do you charge more if you use a used toilet brush? Maybe that's a bad joke, right? Go ahead. Here you've got cotton, cotton, cotton. Orange cotton, white cotton, orange cotton. Running stitch to tack it down, laser to cut it, and when you wash it, it's going to flower up. So if you want to do the color of a flag, etc., and do red, white, blue, that's a cool trick to do. Go ahead. Now, this is a great example because this is a total embroidery nightmare. You've got a thin, let's say, dry wicking shirt, which is very difficult to embroider without puckering. You've got a big body of material, which takes a heavy stitch count, and it immediately branches off into next to nothing. The next to nothing is so much of a nightmare to try and embroider to make it look good that most people won't achieve something that looks excellent there. And if you farm it out, it's even worse sometimes. Now add to that, I've got the in-between area of the legs of the lamb, which is reversed, so I've got these little chunks in here. I've got serifs of fonts that are narrow and curved, and then I've got a tiny font underneath it. So some people are sticklers about their logo. If you give it to them tone on tone as a laser etch, you do what's impossible with embroidery, but you do it in seconds with the laser. Flip. When you do things that are natural in etching, we call it eco-etching, and what happens is natural things get lighter. So on a black shirt, I remove the color, navy blue, red, I remove the color. On a very light natural, I make it darker, and it's almost exclusively always a coffee stain. Notice here that by changing the density of the vectors, I can change the color, and I can make three-dimensional look and shape, etc. So it's about grayscales essentially. So anything natural gets lighter. In the case of a natural colored product, it gets coffee stain color. Synthetics, they always get darker except for white and black. You can't make black blacker, and there's no color to extrapolate from white. Go ahead. One more time. So here's an example where when you have a scanning laser, you're shooting from a distance, and because you're working on the surface of a curved item, you can get a good portion of the surface curved. So here you see an outline of the logo. Here you see the fill of the logo and the reverse of it. So this one takes longer to etch than that one, and then even though it looks oval, it's actually a wooden coaster or cork coaster that you put it on. So you can make unique gift objects, gift packages with a laser. This is flask stainless steel, and it was treated with a spray, and that spray reacts with the laser to create blackness, and you wipe it off with water, a sponge, etc. So this is what we call a wall of fame. These are all applique decorations, all full front. And if you can take a look here, the Michelin Man was made with one piece of felt, and you basically did running stitches to attach it, the laser cut, you peeled off the excess. The trick in embroidery is instead of trying to clean out little areas, what you can do is you can fill stitch the black eyes and in between the fingers, so you don't have to fool around cleaning areas. You can use different materials. This is tackle twill 4-color. This is tackle twill with felt. This is felt alone. This is tackle twill alone. There's tiny little letters up there that would be a nightmare to stitch. The stitch count would be high, but if you just do an outline and stitches, it's very easy. Up in the top left corner, it's interesting because you put a piece of fleece underneath a piece of fleece, and then you sew down, you've got fluffiness. So you've got 3-dimension happening there. The KFC logo that's world-renowned, that's 2 pieces of felt. That would be a complete nightmare to do. So everything but the Bugatti stitch out here is under 2,200 stitches. Everything is full size. So there isn't a person in the room who has an embroidery machine who can actually do this large logo in stitches, and you couldn't do a left chest logo on average, or 5,000 to 8,000 stitches, with less than this. Shoot. There's that Michelin Man. So this is filled in with this fill stitch, fill stitch, fill stitch, fill stitch. This area is the space of the black shirt behind it. It's cut out felt, so it's 3-dimensional. This is all tackle twill. Now, there's a couple ways to approach this. One is, in this case, you did green tackle twill with black on top, and then white on top of everything. So it's a 3-layer process, basically. You could, if you have dark material underneath, have left that out, but it looked cool to have all the same shininess with the tackle twill. And if you wanted to, you could have tacked this down with some simple satin stitch to make it look quick. But you don't want to. You want to have it either all satin stitch on the inside or not, because you want to make it all even dimension there. Go ahead. Cool idea. A lot of you people have direct-to-garment printers. Almost everybody in the room pretty much has a heat press. You can buy heat transfer material and get it in low quantity, but transfer, let's say you have a school, and this is University of Georgia, and it's a football theme, and those are the colors. You can take football helmets and footballs and heat transfer them onto a cotton t-shirt, but then you can put that underneath your t-shirt or your sweatshirt, and when you do the running stitch, you can do a reverse applique, thereby exposing the print that's underneath. That's like a super simple idea that's multimedia that nobody without a laser technology could do, for example. So it opens up a huge gamut of things that were impossible before. This was a case study. It was interesting to see that I've got 1, 2, 3, 4, 5, 6 items here. They're all full front. There's reverse applique, there's 2-layer applique, there's t-shirt applique on a zippered hoodie. You've got cotton twill, not tackle twill. Cotton twill is the one that disintegrates really quickly and gets all fuzzy. And you've got male and female by pink and dark colors, etc. And if you shoot, I think the next one has some prices on there. So what do you pay for a shirt, a sweatshirt here?
Depends on the brand, maybe 30, 40 pounds for a good quality.
Just for the blank.
Oh, just for a blank, 5 pounds. 5, 6 pounds.
So 5, 6 pounds would be, you know, under $10, maybe $7, $8 tops for a good quality one. And here you've got something selling for $60, for $50, and they're less stitches than a left chest embroidery. So how can you go wrong if you change what, you know, 95% of the people in the market can't do, and you do something different? And here you've got the, sorry, you had the placement there, it's fine. You had the placement which is on the left side on the zipper, etc. So the weakness of the laser and the laser user is fear of the technology, the unknown. People are terrified. They have to meet certain safety standards or else they can't be on the market. So that's pretty much taken care of. The supplier will teach you how to avoid stuff, how to take care of it, how to maintain it. And the word laser is a little bit like car, right? Because it's so versatile. Typically the laser is the tube inside the machine, but we refer to the whole machine as my laser. The big problem is customers can't ask for something they don't know anything about. That's your fault for you not educating your client. That's you, being too busy with existing clients and not sending something out. Requires you to do basic marketing 101 work. If they don't know, look in the mirror because you're not doing the job that you need to make them aware. And it's as simple as making a sample, getting it out to your best customers. If you've got 10 or 15 customers that are great, then send it out once a month to those 10 or 15 customers that are really great. With regards to etching, a negative is that a black synthetic product doesn't get darker. But you've seen, let's say if you've been by my booth, for example, you can etch black and it does show a shade and it's a very subtle decoration. You can do navy blue and it almost comes out black. But synthetics don't get darker. You can't take a white, a pink, or a baby blue synthetic and make it lighter. Naturals, remember that they look like discharge. So a black, navy blue, red t-shirt gets the color taken out. When you wash it, it has a grayness like it was bleached exactly to the logo. Go ahead. Strengths of a laser are, we live in an iPhone, internet age. We need information instantaneously. Embroideries have been the same technology for the last 40 years. It hasn't changed. It's still sewing. It's quieter, it's faster, but it's still stitching. And when you would add a laser like that's in harmony with your embroidery machine, you're basically taking your embroidery completely out of the industrial age. So you can take an old 1986 machine, a 1999 machine, whatever the case is, with, I don't know, 5 colors. You're only going to, in all the designs that we went through in the examples here, they're all basically, 2, 3 colors. They're just a bit of running stitch, a bit of zigzag stitch, tack down stitch, contrast stitch, but it's not 9, 10 colors. So you take old equipment and you completely revitalize it. You drastically reduce stitch count. When you lower stitch count, you end up getting more turnover per hour. So your increased turnover on average in existing embroidery is 4 to 6 times more. Why? Because if an average left chest logo takes 5,000 to 8,000 stitches, the problem is that you can only do so many pieces per hour, which limits you to that North American standard of $35, $45 per hour. That's not my number. That's the numbers from the banks and the leasing companies looking at the financials of you people when they're financing the equipment, telling us, listen, these people don't earn more than that. We can't give them more money. That's not my statistic, by the way. When you have a laser and you have less stitch count, you have less wear and tear because you have less motion, less movement, less mechanical stuff on your embroidery machine. And because it's at the infancy stage, working towards critical mass, when you're getting in the market now, you're going to be on the rise. Embroidery is at capacity, it's at saturation. There's always somebody who can do it less than you and somebody that can do it less than them. So there's little competition, but you have to make your customers aware. Oh, I see how I got lots of strengths of laser. Wow, okay. Well, it's a laser seminar, right? Why wouldn't I be positive? So, the summary is a very little competition. The cost of entry is higher than DTG or screen printing, when you get a scanning or a Galvo laser. But your margins are also way, way higher with less competition. It's subtle tone on tone. It's popular for corporations because if you look at many of you people in your embroidery business, a lot of the stuff you do on a black shirt for Coca-Cola is a gray Coca-Cola, not red and white anymore, okay? Extremely quick output. So when you've got no stitches, you're hitting 180, 210 pieces per hour. It's very profitable because at a low volume you can do 12 pieces, but when you get $6 a piece, $5 a piece, and it takes you 7 minutes, You know, we've got video and samples and demos where you will do 4 pieces in a minute, blindfolded practically. I'm joking about the blindfolded, but you'll hit that number. So you're, at that volume, you're getting $6. So you can do a 12-piece order and in 10 minutes be completely finished, from digitizing to output, done. Typical left chest for anything etching is $3.50 to $6. Typical full front wholesale is $5 to $7.50, but it's only 2,200, 1,800, 1,600 stitches. When you retail that, and retail to corporate, that's a $9 to $16 markup. $9 to $16, sorry, end user. Okay, $7 to $9.50 wholesale. Unique placement options, so you can do arms and collars and yokes and plackets and the little fine area below, you know, the seams, all that. You can do it on the inside. You can label on the inside of every shirt that goes out, so every product has your brand where it was decorated by. Right? Woo! I tried to do it as fast as possible. Now what you can do is ask any questions that you want, and I will answer them. So I will turn off the blinding light and walk to the middle of the room with the microphone. I'll ask some questions. Fair enough? Thank you very much.